He is currently the lead firmware engineer for KeepKey, the hardware wallet provider that was acquired by Shapeshift. And so please welcome John KeepKey, not his real last name, obviously, to the stage. And also, this is going to be a bit interactive. Sorry, I forgot to say that. So if anyone wants to participate in the interactivity, just raise your hand. I'm going to pass out the KeepKey devices. Yes.
Cool. Come on, slides. So this is a follow-on along talk. You're going to need the slides to make that work. So go download them if you can. So what to expect? In this talk, we're going to go over a couple of different ways of talking to hardware wallets, and it's going to be back and forth between some lessons and then hands-on examples, talk about it a little bit, more lessons, more hands-on examples, etc. Getting the slides. So clone the repo, CD into it, yarn start. And then you'll be thrown into web browser with the first slide, and you can use the arrow keys to get to whatever slide we're on. You're going to need an up-to-date KeepKey, which I handed out, shortcut that part. And it will help if it is initialized, which those have the 12 alls seed on them. So getting into the talk, there's a problem we have in the hardware wallet space where every time a dApp or a wallet or some client integrates one of the hardware wallets, they have to do it over and over again, once for each of the interfaces. So say this dApp wants to integrate Ledger and Trezor, they have to pull both of them in there independently. Likewise for each and everything. And that's kind of inefficient. So it would be better if there was this kind of common API in between them all. So wallets can integrate the one thing, and then hardware wallets can go integrate the other side of it, and everyone's happy. We built that at Shapeshift because we needed it for our new platform. The architecture of this is built up of a handful of different packages, one for each of the transports for the devices, and then a layer for kind of matching the abstraction between like what is an HD wallet and what is a hardware wallet, and then some like core utilities that glue it all together. So this is the first exercise. Any of you guys got the slides up and running on your machines? This whole library is called HD Wallet, but that's something different than HD Wallet. Naming is hard. Node 10. Yes, you will need to do that. Maybe? I don't know. I'm a firmware dev. So what I was going for in this slide was like, let's plug a device in and like try out this pair KeepKey button. And then you can see, hey, this thing wants to connect. Pair a device, and then a nice little thing will show up in the UI saying, hey, you did it. And you could do the same thing with a Trezor or whatever. The other thing that I wanted to talk about here is in this constructor we set up this keyring, which is where kind of all of the hardware wallets and otherwise come together. And then we plug these adapters, one for each wallet, into it so that we can ask when I want to initialize a hardware wallet or like grab one, you ask the adapter for it, and it'll put that in the keyring. Next thing I wanted to talk about was some feature tests. So there's a lot of kind of biodiversity among hardware wallets where each one supports different feature sets. So we needed to unify across that whole space of features. Let's go back to the pair device one so you can play along. And I can show all the rest of you now that I have my device in what happens. So you go to there, you pair your device, you connect. Where was I? So feature tests. We have various bits of this API that show up when a given hardware wallet supports a given feature set. So say ETH-like networks, then if that device is there or has ETH support, then we'll get all of these ETH methods on that wallet. Likewise for UTXO coins, if that wallet has it, then we'll get the methods for those. Next thing I wanted to talk about was BIP32 paths. Since this is a wallet or a library for interacting with hierarchical deterministic wallets, you're going to see paths everywhere. These paths have two representations. One of them is, and I can't see the mouse, but this string representation, M44 prime, whatever, or the integer versions of that, where the highest most bit representing the prime. For BIP44, these have the purpose, the coin, the account, the change, and then the address index. And that works all well and good for UTXO coins, but unfortunately it turned into a massive mess on Ethereum since everyone chose a different standard for where to put the ETH address in the HD tree. So what do you do about that? Well, let's ask HD Wallet. So we added a API call to say, where does this wallet prefer to put things in the tree? And if you ask it, you get a list of paths. Next thing you might want to do is show an address on the device. And this comes with an interesting challenge because one of the APIs that we integrate with to sign for Trezor, if you're going to show an address, you have to have an address for them to compare with. And so what do you do here? Solution to that, let's ask twice. So first we ask with, nah, I don't want to show it on the device. Grab the address, render the QR code or whatever it is, and then ask again with, yes, I want the user to see this. So let's try that out. Who's still following along, trying it? Do you all want to like crowd around his machine and play with it? Because mine, the font is probably too small to be useful. But we can do it on mine. So what you'll do here is go look for this handle show button or function. And how much time do I have? That's counting down 26. So let's take 10 minutes on this. Okay. And there's some docs at the bottom here. If you leave the page and then like come back, you'll lose your state. So open them in a new tab. and basically follow all the to-dos in here using what we learned in the previous slides. So that was showing an address. Let's move on to talk about how Ethereum transactions work, or more specifically, ERC20 transfers. So an ERC20 transfer looks like this. You've got the method that takes the address you want to send to and the amount that you want to send to the other guy. Tiny font, kind of hard to read, but whatever. We've got the method hash, which is kind of the hash of this function signature. Then the address we're sending to padded to 32 bytes. And then the amount that we're sending in way as a 32-byte integer. And here's what the signing API looks like. Kind of similar thing to get address. You pass a bunch of stuff and then it asks the device like, hey, let's sign a transaction. And maybe the device will ask back for, oh wait, I need a PIN because I don't trust you, or I need the passphrase. And all of that is handled under the hood by the device or by the library. And as a library user, all you have to worry about is, I want the signature out, and here's all the stuff that I want to pass to it. So on the next slide, let's go try out that transaction. We've just got the thing from the other slide and uncomment it. And if I thought ahead, I would have brought some candy for the first person to tell me what this transaction does. All right, let's talk about message signing. A little bit different than transaction signing. So maybe you want to prove that you own an address without sending money out of it. And you might come up with some naive way to do that, like let's just take the hash of the message and sign it with a key. Well, that kind of has a problem with it, because what if someone gives you a message that is a transaction, and then you're signing something that sends them all your money, which isn't great. So what the Ethereum devs came up with is they prepend this thing to the beginning of the message before hashing it to say, this thing can never be a legit transaction on the network because it's got this stuff at the beginning of it. And this is all the user cares about signing, so it's good. And that protects hardware wallet users from accidentally signing personal messages for things that would steal money from them, but still lets them make commitments to that they own their address, or like prove it. So we have support for this in our API. You can play with sign message, which takes the address end list again, message you want to sign. And then likewise for verify message, you pass in a message and a signature, and the device will check behind the scenes whether those line up. Something interesting about our API here is not all hardware wallets support all of these things. So, for example, on Ledger, we don't have a way to verify on device. And so we just implemented that in software. So you can't trust it quite as much as you could on a KeepKey or a Trezor, but maybe good enough for your purposes? I don't know. Depends on what you use it for. Next, let's talk about UTXO coins. Similar thing to on ETH addresses, where you got to do that like ask twice pattern. This time you got to also pass the script type. So that's whether it's a like a legacy address or the new hotness SegWit stuff. And you can also pass which particular UTXO coin you're doing. So if you get like an M address for Litecoin, or if you want a 3 address on Bitcoin, that would affect that. So for transactions, the process is a lot more involved, and we kind of let you do what you want, which means this library isn't going to help you with UTXO selection. That's kind of like up to the client. You can use some other library for it, or an API service, or whatever. And an interesting thing to note is that for legacy UTXOs, you need to provide the entire previous transaction, which KeepKey and the Trezor use to prove that the amounts add up. And then last slide, some take-home exercises if you want to play with it later. That's all I had.